Hi there. Welcome to lecture 24 of Machine Learning from Data. And we're going to continue talking about this optimal hyperplane, this fattest hyperplane that fits the data, that's most robust to measurement error. In particular, we'd like to discuss, why is this fattest hyperplane the best? Is it just intuitive, or can we put some meat into that statement? And once we have handled this issue, then we made this assumption that the data is separable, so we'll have to discuss, what to do when the data is not separable. Now, quick recap of what we did last time. So we introduced this concept of the optimal or the fattest hyperplane. And here's a toy example with 4 data points, two red X's, 2 blue O's. Okay, and this fattest hyperplane has a maximum width, a maximum margin, and that's illustrated in yellow. Okay, and we showed how to solve this specific problem by hand. Okay, and when we talk about can we efficiently find this fattest separator, we reduce the problem to quadratic programming. Okay, so specifically, the algorithm in what's called the primal form is to minimize the norm of the weights. Now remember that we separated out the bias, so we are minimizing only the norm of the feature weights, minimize the norm of the feature weights, subject to the constraint that you separate all the data. And we discussed this notion of separation where y times w transpose xn plus b should be greater equal to 1. So without loss of generality, that's what it means to separate the data. And, when we do this, we find that, basically what's happening is you put this separator and then you increase the margin as much as you can, and the optimal separator increases the margin, to the largest possible width. And when you've obtained this optimal separator, as you're increasing the margin, as you're increasing this cushion, you will simultaneously hit a red point and a blue point, so a point on each side an equal distance away, and then you've got the width of this optimal separator. Okay. And then when this happens, there'll be some points on the cushion that are right on the cushion, illustrated here with boxed red X and blue circle points. Okay, these we call support vectors, and the interesting observations are the support vectors seem to be the important data points, but even more interesting is that if I throw away this other data point, or all data points other than the support vectors, basically the optimal separating hyperplane doesn't change in any way, and its width doesn't change, and its position is not going to change. So all you need are the support vectors in order to sort of recover this fattest optimal hyperplane. Okay, so that's the algorithm. It's quadratic programming. Mathematicians know how to solve this problem. Okay. And I showed some examples on, actually this is a toy data set where you have a target function, you generate red X and blue circles, and here's the optimal separating hyperplane with its width. The gray lines are the sort of thickness, the cushion, okay, and the support vectors are boxed, okay, and its out of sample error is some fixed value. Now, if you run the PLA, depending on the order of the points and depending on which point you pick as your misclassified point for each PLA update, you end up at a separating hyperplane which could be quite variable, and so you get a distribution of out of sample errors. Some of them can be better than the support vector machine. Some of them can be better. If you're lucky, you get a better. If you're unlucky, you could be much worse. Okay, the support vector machine is nice, deterministic, and has this nice property that it's as fat as you can get, which means that it tolerates the maximum amount of measurement nodes. So today, let's start by trying to address, is fatter better than thick? So that's what we're going to address. We started this a little bit last time by building this link between the fattest hyperplane and regularization. So, when all is said and done and we look at the algorithm for obtaining the optimal hyperplane, we minimize the norm of the weights. So we minimize the norm of the weights, subject to fitting the data. That's sort of what Occam said. Subject to explaining the data, get the simplest hypothesis. It's literally Occam. Okay? And that's what the optimal hyperplane is implementing. Okay, when we studied regularization, we were minimizing the in-sample error subject to a budget on the weights, subject to a budget on their complexity. So in some sense, you can view this optimal hyperplane as maximally regularized, providing that you can explain the data. Okay, and now and later today we'll discuss what happens when the data is not explainable, okay, and how do we sort of extend this algorithm to the situation where you cannot find a linear separator. Okay. So in some sense you can view this optimal hyperplane as performing automatic regularization, automatic maximum possible regularization, providing that you require me to fit the data. Okay, so we're going to start by addressing the question of is the fattest hyperplane better? In other words, is it generally speaking better to separate the data with a large margin than with a small margin? Okay, so we'll provide 3 justifications of this. The first is just experimental. We'll run an experiment where we, pick a separator and we see what happens if on average when the separator has a large margin or when the separator has a small margin. And I'll show, results for E out and results for the bias and variance. And that'll be pretty convincing on its own that, yes, larger margin seems to be better. Okay. Then what we will do is we'll show that indeed you can take fat separators, okay, compared to thin separators, and you can show that the VC dimension can be bounded by something that can be smaller than d plus 1. So d plus 1 is the VC dimension of the perceptron model, which corresponds to the thinnest possible separators. Okay. We can show that fat separators can have a smaller VC dimension than thin separators, which then means that the link from E in to E out is better. Okay. So that's a little bit of theoretical evidence for why fat or large margin separators are better. And finally, we will do something that's quite interesting, okay, and it's going to have an impact on what we discuss later, which is that we will get a bound on the cross-validation error for the optimal hyperplane. That's going to be a very interesting bound. Okay. It's going to be a bound on the cross-validation error that does not explicitly depend on the dimension of the space. That's going to be very interesting. Now remember what the cross-validation error was. You leave out a data point, you build your model, and then you classify the left-out data point, and on average, what's the error that you make on the left-out data point? So the cross-validation error is an estimate of the out-of-sample error that you expect to make, or it's an unbiased estimate of your expected out-of-sample error when you learn on n-1 data points. So at a high level, the cross-validation error is an estimate of your out-of-sample error. And we will show that for this optimal hyperplane, the out-of-sample error, it turns out, does not depend explicitly on the dimension. You can get a bound for the cross-validation error that is dependent only on the number of support vectors. Remember what those support vectors were? They were the points that are on the margin, okay, that lie on the margin, that prevent it from expanding more, the important data points. So, 3 pieces of evidence that allow us to get a handle on the sort of generalization and overfitting or better regularization capability of the optimal hyperplane, this fattest hyperplane. Okay. So let's begin with some experimental evidence. Let's start with some experimental evidence that suggests the fat hyperplane is better than the thin hyperplane. And the result of an experiment is shown on the right. Let me briefly describe the experiment. Okay. So here's the idea. Generate a separable data set. Generate a separable data set. And we used n equals 20. So now, this is not, a proof that fat hyperplanes are better than thin hyperplanes. This is just some experimental evidence. So most of the details are not that important. So, follow the gist. Okay. The second step is, okay, now that we've generated a separable data set, generate, so that there'll be many possible separating hyperplanes, randomly generate 50,000. So that's what the experiment that we ran. Randomly, and I'll put this in quotes. There's a question of what does randomly generate a separating hyperplane mean? Does it mean it's separating with varying shift? Can you also alter the angle and so on? But the details are not so important. The idea is what's important. So randomly generate 50,000 separating hyperplanes. Okay, so I have some separable data. I randomly generate 50,000 separating hyperplanes. And for each such hyperplane, okay, so I have hyperplanes H1, H2, up to H50,000, 50K. Okay, so each such hyperplane has a fatness, the distance to the closest data point. So let me call that, gamma of H1. I can compute gamma of H2 and so on, up to gamma of H50K. And now, once I've generated this data, I can compute the fattest possible separating hyperplane. We call that the margin of the data. So, and I can compute the ratio, the ratio between the fatness of the random hyperplane and the fattest possible, the optimal. So let's call this gamma of H1 divided by gamma opt, divided by gamma opt, divided by gamma opt. Let me call this rho 1, rho 2, up to rho 50K. Okay, so this is basically what fraction of the margin available, what fraction of the width available did your random hyperplane capture. Okay, and for each hyperplane, since it's a simulated setting, I can compute E out. Okay, I can also compute E out of H1, E out of H2 da E out of H50K. Okay, so now I have the fraction of the margin captured and the out of sample error. When the fraction of the margin captured is 0, that means that the random hyperplane is basically sitting very close to one of the data points. So its width is close to 0. When the fraction of the margin captured is close to 1, it means it's nearly optimal, nearly the fattest possible separating hyperplane. Why am I normalizing by the maximum available margin? Is because I'm now going to repeat this many times. So repeat by generating many data sets. And so by comparing the margin you captured with respect to the maximum available margin, that sort of, puts each data set on an equal footing. We're viewing each data set through the lens of what's the maximum available margin. Okay, so the margin captured by a random hyperplane as a fraction of the available margin, we can plot on the x-axis. Let's call that rho, goes from 0 to 1. And on the y-axis, I will plot the average, out of sample error among those hyperplanes which captured that amount of margin. So E out of rho. Okay. And, the optimal hyperplane, we can call this the support vector machine, attains a certain value of E out. Okay. And the typical, and so versus rho, we can look at what the out of sample error is, and that's what that plot on the right shows. Okay, so it's real data. We really did this experiment. And what we see is that if the random hyperplane captures a small margin, its out of sample error tends to be large, and as it captures a larger and larger margin, its out of sample error tends to drop. Okay, and something interesting happens at the end here, where it turns out that, it continues to drop as you capture a larger and larger margin, but then it starts going up a little bit, at which point, you get to the out of sample error for margin equals 1. That's the optimal hyperplane. Okay. This is interesting, and, this is sort of suggesting that, going purely for the maximum margin is not completely the best thing to do, but it clearly shows that bigger margin is better. We may conjecture what's going on here. Basically what's happening is the optimal margin just looks at these few support vectors, these few data points that define the fattest separating hyperplane. And what this is suggesting is that those other points might also be able to contribute to lowering the out of sample error. Okay, which means that if you want those other points to contribute, you have to pay some attention to them, not just the support vectors, and that will result in a slightly, thinner hyperplane that pays attention to some of the other data points. Okay, so it's a little bit interesting when you get to close to 1, margin, close to maximum margin, but there's clear evidence that larger the margin, the better the out of sample error. Okay? So fatter margin is better with respect to learning, with respect to what we care about. And we knew that from the intuition. It's more robust to measurement errors. Okay. Let's look at another experiment. So there's no harm done in looking at experimental data to justify intuition and theory. You should always do this. Let's look at the optimal hyperplane from the perspective of bias and variance. Okay. And I'm doing a simple experiment. So again, just to show you some evidence for how the fatness of the hyperplane, or how the fattest hyperplane is helping us. Okay. So here's a simple experiment. I simulate a simple learning problem in which I have a flat target function, and on top it's +1 and the bottom it's -1. So here's +1, I generate a few data points. Okay, and the bottom it's -1, so I generate a few data points. Okay. Now, I'm going to try to separate this data again with flat hyperplane. So that's my hypothesis set. And what we're interested in is the margin of this hyperplane. Okay, and the fattest hyperplane is obtained by picking the flat separator that sort of bisects the distance between, the vertical distance between the lowest blue point and the highest red point. So that might be something like, this hyperplane, this flat line here, plus above, minus below. And so this is its margin, or this is its cushion. Okay, and that's the width. Okay. Now, if I'm generating a random hyperplane that separates, that random hyperplane can be anywhere, between this blue and this red. So anywhere, any flat line between this blue and this red, the optimal fattest hyperplane is always going to be this one. Okay, now I generate random data points, random data sets. I generate many of these data sets, and I can look at, where is the optimal hyperplane and where is the random one. The random one will play around in this region. And as the data set changes, that region can either get larger or it can get smaller. Okay, and what's shown in the bottom left, okay, is, where is that optimal hyperplane? And on the right we show the frequency that the optimal hyperplane is at that point, and where is the random hyperplane. So in blue is the optimal hyperplane. Okay? And so if this is 0, so this is 0 where the target function is, both random and optimal are symmetric around 0 because it's equally likely that your data points are more skewed towards the bottom or the top, and that will generate separating hyperplanes skewed towards the bottom or the top. Okay? So the optimal hyperplane is most likely to be close to 0, so this is 0, and then it's dropping. Okay? It's very rapidly dropping. Okay, beautiful. Okay, so that's the optimal hyperplane. Maybe it's a little bit taller here. No. Something like this. It drops pretty rapidly. What's happening with the random hyperplane? So the random hyperplane, again, the most likely random hyperplanes that you get are concentrated around 0, but they're slightly lower probability than optimal, so they're something like this. Okay, but the distribution is a little bit fatter. Okay, it goes a little bit wider. And that's because, it's a random hyperplane, so it plays around a little bit with that extra, width that's available to generate a random hyperplane. So it looks more like that. So what do we observe? On average, both of them give close to the target function. So their biases are going to be comparable. But look at the variance of the random hyperplane. And no surprise, the optimal hyperplane is this deterministic bisector of the lowest blue and highest red vertical distance. But the random one has variance. Okay? And that's shown in where the hyperplane ends up separating the data from. Okay? And so we expect that the optimal hyperplane will have a comparable bias and much smaller variance. And indeed, you can see in the table there. Okay, indeed, actually, the bias of the optimal hyperplane is slightly lower, okay, but the variance is much lower. And then remember, for classification or regression, squared error, the out-of-sample error is the sum, bias plus variance. So the optimal hyperplane wins. It wins mostly because it lowers the variance a lot. Now, let's think back to regularization. How did regularization work? Regularization was constraining the hypothesis set, constraining the fitting of the data, okay, and in doing so, it considerably reduces your ability to overfit to the noise, considerably reducing your variance, and hopefully the side effect, the bias, wasn't getting too much worse. Okay, so that's how regularization worked. Well, the optimal hyperplane significantly reduces variance, okay, and even can improve the bias. So it's even slightly better than the standard weight decay regularization. Okay. Doesn't really hurt the bias, not much side effect at all, but shrinks the variance. So there's no reason not to use it. Okay. And indeed, okay, we already sort of had a sort of idea that the way that the optimal hyperplane is helping us is by allowing us to tolerate noise, i.e. becoming robust to noise, i.e. that's what regularization did. And now we see it even in the bias variance analysis. And it has the same effect in some sense as regularization. Okay,